consider the LRC circuit that's shown, and we're going to assume that the capacitor is initially charged to an initial amount Q naught. Okay, so Q is going to be a function of T, and at Q0 then the plates are charged to initial amount Q naught. Right, so basically what we've done is we've hooked the capacitor up to a battery, say, given it some voltage, and then placed it in this circuit with this open switch. And we want to know what's going to happen when I close the switch. Right? So ignore that now. So now current is going to start flowing through the circuit, and current is going to be flowing everywhere all at the same time with the same value. But if you recall our discussion on the LC circuit by itself, the presence of the inductor acts to cause a sinusoidal oscillation in the current. So it actually produces AC current. What's going to happen here, though, is that the resistor is going to be dissipating the power that's delivered to it. So the capacitor and the inductor don't dissipate the power. They store alternately rather, the energy in their electric and magnetic fields, and the strength of those fields change as the amount of current changes, but the resistor actually dissipates the power. So the resistor is going to be acting like a dampening mechanism. Right, and let me actually drag this slide to the top. I forgot to do that. All right, so we're there. And so with that in mind, R is going to act like a dampening mechanism. So the oscillations aren't going to just keep going. They're going to start, and then depending on the strength of R, if R is not very big, you'll have a sinusoidal oscillation with an exponential decay, something that would look like maybe a little bit something like this, right? And you would get an exponential decay curve to sandwich those. But if R is at a specific value that we call the critical value, then the oscillations won't keep oscillating, right? You won't get oscillations, multiple oscillations, I should say. And then if the resistor is larger than that critical value, then you will get the current will just simply die off. In other words, if the resistance is too high. So you'll have all these different options. But how do we figure out what's happening mathematically? Okay, so we've looked at an equation like this before, but just to kind of rederive it, let's actually start up here. So remember that when I'm just looking at the energy in the inductor and capacitor, this is going to be 1/2 Li squared for the inductor plus 1/2 C. Let's use the alternate. Let's use this one. Okay. So using this definition of the energy, if I take the derivative of this with respect to time, right, then this is going to be Li di dt, and take the derivative of 1/2 q squared over c. This is going to be 1/2. The 1/2 is going to go away with the differentiation of the q. and this is going to become Q over C dq dt. Okay, but the dq dt is just the current I, so this turns into Li di dt plus Q over C I. Okay, and the Q here also represents the charge on the plates. So I apologize for the notation for using lowercase q here and capital Q here. It's just habit when you're writing out the energy of the capacitor plates. It's habit to write it in terms of capital Q, but they mean the same thing. But so this is the energy. This is the rate at which the energy changes in the inductor and the capacitor. So the rate at which the energy changes in the inductor and capacitor must be equal to the rate at which the energy leaves the resistor. Okay, and so we're going to put a minus sign here to indicate that the energy is being dissipated, if you will. And I have the instantaneous value of my current everywhere, so I can get rid of one of those. So the total change in energy per unit time I can write down like this. And I'm going to move to lowercase now, since that's what I have in my picture. Lowercase q. Okay, now this is a differential equation, and I can solve this differential equation, and in fact we've already solved this differential equation, right? We already did that in a previous video. But what I want to do now is understand how the charge on the plates is going to change. So remember, I've got my current is equal to dq dt, so di dt is then the same thing as d squared q dt squared. So this can be written as L d squared q dt squared plus dq dt r plus q over c. So now this is a bona fide second order linear differential equation. Now solving this particular equation is beyond what is necessary for introductory physics. Okay, but I want to show you guys the process by which we will do so. Okay. So here's the method. First of all, recall that Q is a function of time. Okay. Now, there's a principle in differential equations that says if you find a solution to a problem and it works, then you found the solution to the problem. Okay, so no matter how it might be written, and you can sometimes write things in different forms, they can look a little bit different, but they're describing the exact same thing. Okay, and this is true especially when you impose conditions on your system. Okay, you can have a family of solutions, but as soon as you impose conditions on your system, then you will get one unique answer, even if that answer might be able to be written in different ways. For example, you might write it in exponentials, or you might write it in sines and cosines if that's appropriate, or you might write it in hyperbolic sines and cosines if that's appropriate. So you can write these things in different forms, but there's one unique solution. So what we do is we're going to assume, okay, that I can write my function q of t in the form of some constant times e to the rt. Okay? And r is what is going to be known as an eigenvalue. Okay, now we don't have to worry about what that means right now. But r is just a number that I want to solve for. Okay, r is just a parameter that I want to solve for. And if I can write my solution down in this form, then all I have to do is find r and evaluate the constant, and I've got my solution. If it turns out, and it turns out that it will because this is a second order differential equation, second order differential equations typically have two eigenvalues. So what this is actually going to be written down as is the first constant times e to the first eigenvalue times time plus c2e r2t. So the point is to try and find r1 and r2. Okay. Oops. That should be a subscript. Okay, so we're going to try to find R1 and R2. So here's how we do it. If Q is written in this form, okay, if Q is written in this form, and by the way, you can actually kind of combine these, but for the moment, let's just say that Q has the form of CE to the RT. Okay, so we're not going to worry about the R1 and the R2 and things like that for the moment. Differentiating them through would actually give you the same result. It just would take more algebra because you're now doubling your terms. So Q can be written in this form. The first derivative of Q would be R times CE to the RT, and the second derivative would be written as R squared CE to the RT. So I'm going to insert this, and this into my differential equation. And doing that is going to yield L times R squared CE to the RT plus R times little r CE to the RT plus 1 over C from right here times Q, which is C to the or CE to the RT. Now the C's in the functions of Q are just constants. Okay, and perhaps I should have used a different letter so it wouldn't get confused with capacitance. But I have this, and the point is that my CE to the RT function is found everywhere, and so it cancels out, and I'm left with L times R squared plus the resistance times R plus 1 over the capacitance. And now this is a quadratic equation. Okay, so it turns out that if I can write my solution as an exponential solution, then the values for r that I'm looking for turn out to be the roots of a polynomial equation. When you're working with a second order differential equation, this will turn out to be a quadratic equation. And therefore, quadratic equations, we know, have two roots. So, what do those roots look like? How do I find them? Well, if you recall, I can write the quadratic equation as a times x squared plus b times x plus c and equals 0. And if I have it in that form, then x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay? So I have negative b plus or minus the square root of b squared minus 4ac all over 2a. And I can identify a with r, or I'm sorry, a with l, b with the, so a with the inductance, b with the resistance, and c with 1 over the capacitance, right? So if I write things in that form, okay, if I write it in that form, then this is going to give me r is going to equal negative the resistance plus or minus the square root of the resistance squared minus 4 times a times c, but this is 1 over the capacitance, all over 2a, or all over 2l. Okay, so this is the description of the values for r that I want to use in my solution. Okay, and you'll notice there are two of them with the plus and minus form there. And so what's going to happen here? Well, the interesting part is right here. Okay, the interesting part is right here. If this quantity is less than 0, okay, then I'm going to get a negative sign in here. And when I take the square root of a negative number, I get imaginary numbers. And so, if this quantity equals 0, then the term drops out, right? Then the term drops out. And if this term is larger than 0, then I won't have imaginary numbers in my exponentials. And so this is what we call underdamped. This is what we call critically damped. And this is what we call overdamped. Okay, so underdamped is oscillations where you have some resistance but not enough to overcome after one cycle, and so you'll get oscillation but with an exponential decay. Critically damped, you'll just get an exponential decay. And overdamped, you get more than just a simple exponential decay, right? But you don't get any oscillation. So that is the way that these solutions work. So now I'm going to write this in a slightly more suggestive form. Okay, so r is going to be equal to negative r over 2l plus or minus the square root of r squared minus 4l over c over 2l. And I'm going to denote this quantity as gamma, right? And let's denote the inside of the square root, what's called the discriminant. Let's label this as beta. And then I've got r is equal to, and by the way, let's not include the negative sign in gamma. So gamma is just RL, or r over 2l. Okay. So, and in fact, maybe I should write that. Let me write it here. So gamma is equal to r over 2l, and beta is equal to r squared minus 4l over c. And then I can write this in the form of negative gamma plus or minus the square root of beta over 2l. Okay? But, so what we want to do is we want to look at the underdamped case. So we're going to assume that beta is less than 0. Okay? So assume beta is less than 0. Then I can write this as r is equal to negative gamma plus or minus the square root of negative beta over 2l. And now this is the same thing as r is equal to negative gamma plus or minus the square root of negative 1 times the square root of beta over 2l. And the square root of negative 1 is I. So r is equal to negative gamma plus or minus I square root beta over 2l. And now let's define beta, the square root of beta over 2l, to be a new parameter, and let's call it mu. So this is really just cleaning up notation. Okay, so here are my roots. So r1 is going to be written as negative gamma plus I times mu. And r2 is going to be negative gamma minus I mu. Okay, so here are the two solutions for the eigenvalues. And now what we can do is plug those in to my overall solution, right? And so what we're going to do is we're going to say Q of t is equal to C1 e to the R1 times t plus C2 e to the R2 times t. So this is going to equal C1 times e to the negative gamma plus I mu, all of that times t, plus C2 e to the negative gamma minus I mu times t. Okay? So, this can also be written as C1 e to the negative gamma t times e to the I mu t plus C2 e to the negative gamma t e to the minus I mu of t. Okay? And so now, here is where the interesting thing happens. mathematically, okay? These e to the I mu t and e to the negative I mu t. You can use Euler's equation, and Euler's equation says this: e to the I of your argument, whatever it is, okay? E to the ix, for example. And in fact, let's just go ahead and use mu t, because that's what we're going to be putting in. So e to the I mu t, wait for the pencil to load. I'm not sure why it's not changing. There we go. E to the mu t, e to the I mu t can be written as cosine of mu t plus I sine of mu t. So mu is acting like a angular frequency. Okay, so this quantity is now acting like an angular frequency, right? And if you wanted to, you could put the 2L into the square root by squaring it and dividing everything. And if you did that, you'd get r squared over 4L squared minus 1 over LC. Okay? But this is an angular frequency. And since we have the exponential decays, okay, I can alternately write this in a form like this. I can call this, now we have two constants, right, that are undetermined, but I can factor out the e to the negative gamma t, so this is e to the negative gamma t. And I'm going to switch constants from A to C1 and C2 to A to B, okay? But this is the same thing using the fact that these imaginary exponentials can be written as sines and cosines. I'm going to write this as A times cosine mu t plus B sine of mu t. Okay, so this is the general solution to this problem when the resistance is small enough that it causes the discriminant to be negative. The discriminant to be negative is what actually allows for these sines and cosines. If the discriminant were not negative, we would not get this imaginary number here, and this would also simply be an exponential decay. So you would actually get a set of exponential decays or exponential growths, either one, acting against each other, because in one of the, take the plus, this would be e to the negative gamma t plus e to the positive mu t, and then would be e to the negative gamma t minus e to the mu t. So you would actually have a somewhat complex structure of exponential decay and growth competing against each other. But when you have the negative discriminant, you get the imaginary numbers. That allows for your sines and cosines via Euler's equation. Okay. So now we're ready to evaluate our constants A and B. Okay, so we have to evaluate our constants A and B, and to do this, we need initial conditions. Now we've already given 1. We know that at time 0, the charge on the plates are going to be an initial amount Q naught. The second initial condition, okay, we can actually find or consider. There's a few different ones you could use. You could derive relationships for different ones, but the most obvious one would be what is the current at time 0? Or alternatively, what is dq dt at time 0? Well, when you first flip the switch on the circuit, the current hasn't started flowing yet. When the current hasn't started flowing yet, then we're going to get an initial value of the current is equal to 0. Okay? So we've got, and by the way, this is due to the inductor. Okay, the back EMF from the inductor opposes that current growth, and so the initial amount will in fact be 0. And so, with that in mind, and remembering what gamma and mu are, so gamma was R over 2L, and mu is equal to the square root of R squared minus 4L over C over 2L, right? So our solution was Q of t was equal to e to the negative gamma t times a cosine mu t plus b sine mu t, right? So I can set this equal to 0, at time 0 rather, and at that time, e to the negative 0 times a of cos to the 0 plus b sine of 0 has to equal the initial charge Q naught. Well, e to the negative 0 is of course just 1, so that kind of drops out. The cosine of 0 is 1, so I'm left with a. And the the sine of 0 is 0, so 0 times b is 0. So 1 times a must equal Q naught, so a is equal to Q naught. All right? So now we've solved for one of our coefficients. Now we do the same thing using the second condition. Okay, so first condition, check. Second condition, let's take the derivative of Q, and this is going to be negative gamma e to the negative gamma t times minus a of sine mu t times mu plus b times cosine of mu t times mu, and all of this must equal 0, right? All of that must equal 0. And so I can even go ahead and divide both sides by negative gamma e to the negative gamma t, and dividing 0 by that doesn't do anything. So I can write this condition as negative a when I'm evaluating this at time 0, I can do this, right? So this is going to be equal to negative a, and by the way, I have a factor of mu as well, so if I pull the mu out, then I would be dividing by negative gamma mu times e to the negative gamma t. All right, and all of that cancels out. So what I'm really left with is negative a times the sine of 0 plus b times the cosine of 0, and all of this equals 0, right? But the sine of 0 is 0, so 0 times negative a goes to 0, And this cosine of 0 is 1, so b times 1 must equal 0. So b is 0. Okay, so b is 0. And with that in mind, therefore, this term drops out. That term goes away. And so qt is going to be left with a times e to the negative gamma t times the cosine of mu t. And I won't reinsert the mu here because that's kind of long and convoluted, but this is going to be a times e to the negative r over 2l t times the cosine of mu t. Okay? So this is your general solution. Oh. We've already said that a is q naught, right? So a is q naught. So, and if you think about it, that should make some sense, right? So my function for the charge as a function of time is the original charge on my plates at time 0, then exponentially decays while it's oscillating. Okay, so this is where the solution in the book comes from. Now, I'm going to do an added bonus here, and I'm going to add a Python video that talks about how to do a numerical calculation of this form. Okay? So if you want to investigate this system with a numerical calculation, here's how you do it. Or there's multiple ways you can do it. Here's one way to do it. Right? So the whole idea, computationally, is solve the differential equation numerically. Now there's a myriad of techniques that you can use. One of the most common is called the Runge-Kutta method. We're not going to do the Runge-Kutta here. Okay, I'm going to show you a simpler form, but we're not going to do the Runge-Kutta here. It's a little involved. But the form that I'm going to show you, this is sometimes called the Euler-Cromer method. And the method involves this. Now, the original differential equation looks like this. Okay? The original differential equation looked like this. So here's the method. When you have a second order differential equation, what you do is you say, and now we already know what the first derivative of q is. We know what dq dt is. We already have that. That is the current I. So what we're going to do is we're going to write this in terms of I, and we're going to have L di dt plus Ri plus Q over C is equal to 0. And now I'm going to combine this equation with this equation. And what we're going to do is essentially approximate my differentials by deltas. Okay? So I'm going to let di dt be approximated by a change in current over a change in time. Okay, so let di dt be approximated by a small change in current divided by a small change in time. Well, actually, the change in current doesn't have to be small. The ruling issue is how big a time interval you're taking. The smaller time interval that you take, the closer to the derivative you're going to be approximating. The change in current is just going to be whatever it is, but you can control this computationally, and I'll show you guys how to do that. So I can rewrite this as delta I over delta t plus Ri plus Q over C is equal to 0. And then we have, so we're essentially going to derive a system of equations. And we do the same thing here. So then we let I equal delta Q over delta T. Okay. So these are the two equations that you're going to solve numerically. Now notice, first of all, what we've done. And you can do this for any order of differential equation as long as you know the relationships between your derivatives. What we've done is reduced a second order differential equation down to two first order differential equations. And then we're going to numerically solve those two first order differential equations. We're going to use what's called the difference method. So the Euler-Cromer method relies on using the difference method. Okay, so here's the idea. You know the initial conditions. You know your initial charge and current values. Okay, so these are what we're going to use. These are they're going to be important. Okay, so here's what we do. Let delta I equal I final minus I initial, and let delta Q equal Q final minus Q initial. Right? So now here's what we're going to do. We're going to plug this in to delta I, and we're going to solve for IF. So solving this equation will give me a method that will allow me to solve for the final current, okay, after each time step. So my current is going to get updated after each initial time step. So to solve for IF, here's what we do. So let's look at equation 1. And so I've got L times IF minus I initial divided by delta T. And I'm going to move this quantity to the other side. So this is going to be minus Ri plus Q over C. Now, you'll notice, okay, what values should I and C have since should R and Q have? Since R and Q, what values should this I and this Q have? Since these are functions of time. Well, in this case, this I represents the same thing as the initial current. Okay, the current hasn't changed yet in this term, so this is going to be the initial current, and my Q is going to be the initial charge. Okay, and so continuing solving for IF, multiply both sides by delta T, and divide by L. So this is going to be equal to minus R I initial plus Q initial over C over L times delta T plus my initial current. So now I have an iterative equation that will allow me to calculate these quantities, and then delta Q is QF minus QI. So in fact, let me underline this equation. Right? And then for the current, I have delta Q over delta T is equal to I, and QF minus QI over delta T is equal to I, and solving for QF is going to equal I delta T plus QI. But what value of current do I use here? Okay, if I were to define this as I initial, then this would be what's known as the Euler method. The Euler-Kromer technique, the correction here is to say that I'm actually going to, since I've already evaluated the final current over a very short time step, then it's actually the final current that is more accurate here. So this gets defined as IF. Okay, so for each value of my current, or each value of my charge, I'm going to use the previously calculated value of the current. And so what this means is, if I have specified the value of L, the value of R, and the value of C, and as long, and by the way, it does not matter what my values of L, R, and C are. Okay, the previous derivation was focused on the underdamped, but this method doesn't care. You'll be able to calculate the correct solution for the underdamped, critically damped, or overdamped in any case, regardless of what your values of L, R, and C are. Okay, so this solution, this method actually shows you this correct solution no matter what your type of the parameters of your circuit are. I'll put it that way. It doesn't matter what the parameter of your circuit is. So we have these two equations now, right? We have these two equations. And so to kind of give you a sense of how this works, right? To kind of give you a sense of how this works, the